So today we'll talk about spectral graph theory. So we'll start by last time we saw PageRank, which already hinted at the fact that eigenvalues and eigenvectors of matrices that are defined from graphs can tell you something about the graph. In that case, about the importance of pages that were defined by a graph of links and so on. And then we talked a bit about in general in graphs. So let me just remind the definitions. So we have a graph with vertices and edges, a set of vertices and edges. Sometimes graphs have weights, where I think of Wij as just the weight of edge Ij. And you think if Ij is not an edge, then you can just set, the weight to 0. Now graphs will have very important matrices associated with them. These matrices then we'll see that their eigenvalues and eigenvectors will tell us a lot about the geometry of the graphs. So maybe the most basic, most important matrix is the adjacency matrix. Right, so this is a matrix A, defined the following way. Aij, so I should say A is an n by n matrix, where n is the number of nodes, and it's symmetric. Right? So the last time in the last lecture we saw that right, the PageRank matrix that we defined was symmetric, but most of the objects we're going to see in this course are actually symmetric. Most of the matrices are symmetric. And it's because we think when we think of our graph as n-directed, right? We're going to take our graph to be n-directed. So if there's an edge between I and j, there's an edge between j and I. It won't make sense to talk about edges from I to j and edges from j to I. Right, and the adjacency matrix is defined the following way. Aij is 1 if Ij is an edge, 0 otherwise. Right, this is the same thing essentially as the weight, doubly, right? The matrix of weights. I will use A for when it's a matrix, of an adjacency of a graph without weights, and I will use W when it has weights, which is the same thing. And as we'll see, eigenvalues and eigenvectors of A are going to tell us a lot about the geometry of the graph, right? That's the basis of spectral graph theory, right? The spectrum of matrices is telling us something about the graph. Another important matrix will be the matrix of degrees, right? So this will be an object. The degree matrix will be, again, an n by n matrix. This one will be not only symmetric, but also diagonal. Right? So it's a matrix that only has non-zero elements in its diagonal, and we define dii to be simply the degree of node I. Right? Recall that the degree of node I is simply the sum over all its neighbors of the edges, or if it's unweighted, it's simply the number of neighbors of I. That's what the degree is. And essentially, these are the two building blocks for spectral graph theory. These are the matrices that sort of define all the other matrices. Now, another important matrix that, as we'll see, will be defined from these two, or at least will be able to be written with respect to these two, we'll define it in a different way, is the graph Laplacian. Okay, so the graph Laplacian, we'll call it the graph Laplacian of a graph G, we'll call it LG. LG will be an n by n matrix, also symmetric. Okay. Will be an n by n matrix that's symmetric, and will be the matrix, there's a few different ways of defining it. I will define it through its quadratic form. Right, so it is the matrix that satisfies the following. If I have a vector x in Rn, this will be the matrix that I take x transpose LGX, and this is the same as taking the sum I smaller than j of the weight Wij xi minus xj squared. Right, so why is this matrix important? Well, it's measuring somehow, if I have a signal x or a vector x, it's measuring the difference, the sizes of the differences of xi and xj, right, on the edges, weighted by the edges. So it's measuring how much a signal is not equal in edges. It's measuring some kind of derivative in the geometry of the graph. But in particular, right, a lot of this is going to be about clustering, right? The form of unsupervised learning of the data. I get data, I want to split it into groups. I want to clustering. And the way that we're going to, right, in order to talk about clustering, we talked about cut, right? We're going to, clustering is going to be, the goal is clustering, one of the goals. And in clustering, the idea is to find a set S, subset of the vertices, right? Think of the set of vertices as being like this, and you define S, this would be its complement, and now you measure how good your clustering is by, say, the number of edges that get cut by this. Right? So the cut of S is simply the sum, say, of I in S and J not in S of W by J. Right? So now as we see, this is related to the Laplacian, right? So let's see. Right? In particular, if I take x, right, the vector, to be such that xi is 1 if I is in S and minus 1 otherwise, right? Maybe another way to write this is x is 1 is the indicator at S minus the indicator at S complement. Then I claim that the quadratic form of the Laplacian of this tells me something about the cut. Right? So in particular, right, if I take x transpose Laplacian x, then what do I get? Right? X transpose Laplacian x, by the definition, right? We haven't seen what this matrix is yet. It would be the sum, right, over all pairs I and j of the difference between the squares, the square of the difference between the points, the values of x, and the weight. Now let's see what happens, right? So x is 1 in S and is minus 1 in S complement. So the pairs that where both I and j are either in the same side of the clustering, so they're either both in S or both in S complement, I get 0. Right? Because I get 1 minus 1 or minus 1 minus 1, right? It's just 0. What I will pick up, though, is the places where I and j are in different sides of this cut, right? One is in S, the other is in S complement, or vice versa. And so, in fact, what I will get is something like 1 minus 1, so I get a 2, or a minus 2 squared, so I'll pick up 4. So basically, what I pick up here is 4 times the sum of the weights of the edges that get crossed. So actually, it's not hard to see that this is just 4 times the cut of S. So it's already becoming clear that the Laplacian will have something to do with clustering and cutting the graph. In particular, if I want to find a good cut, something that cuts very little, I should try to minimize this. And minimizing this looks a lot like an eigenvalue problem, right? And indeed, this is sort of the the intuition behind the spectral cluster. Okay, so let's see now what this matrix actually is, right? So let's do a little bit of algebra. So if we write this, okay, ij, and then I have xi minus xj squared. Let's write this in another way. Let's write this as ei minus ej transpose x squared. Right? Where ei is simply the vector that has zeros in a bunch of places, a 1 in the entry I. That is the canonical basis element. Okay, so let's carry this calculation through. Okay, I take this squared, right? This is the same thing as x transpose eij. So I'm going to write this way. Okay. Now I can move next to the other side. Right, so basically, this is the Laplacian, right? The Laplacian is just this matrix. G. It's simply this, and this is basically the most important matrix in spectrography. Right, so let's see if we understand what its entries are like. Okay, so let's see if we understand exactly what are the entries of this matrix. Okay, so for entry ij, right, or ji, you show each pair of entries shows up only once, right, because we only have one I small n j. So ij or ji, they show up just only once. And they show up with the wij, and basically, right, this matrix is a matrix that has a 1 in entry ii, a 1 in entry jj, a -1 in entry ij, and a -1 in entry ji. So in the off-diagonal entries, what they'll get is a -1 times wij. So this means that we'll see minus wij if I is different than j. But now, if you think this way, right, what's happening in the diagonal? In the diagonal, we'll see a 1 in the entry ii and the 1 in entry jj. So now, right, if you think of what's happening for ii, I will sum over all possible j's wij. Right, so I'm getting the degree. Now, it might seem like I'm not getting exactly the degree because I'm only summing for the j's bigger than I. Right, but the other ones will just show up in the entry jj. Right, so if you, I recommend you think about this a little, but you'll see that this is just equal to the degree of I. If I is the same thing as j, right? Or the degree of j. This is the same. Okay, so this is the Laplacian. In particular, right, the Laplacian is just equal to degrees minus the weights. The degree matrix minus the weights matrix. Or, you know, if G is unweighted, then, right, then this is just L equals D minus A. Right, that's why I said that all the matrices basically count. You know, all the matrices that show the spectrograph theory essentially are born out of the degree matrix and the adjacency. Now, you may think, okay, why is this called Laplacian? I remember learning about a Laplacian in Euclidean space, you know, the sum of the pure second derivatives. This is exactly, you know, okay. In a way, it's the same thing. You can talk about the limit of a graph becoming a manifold or even Euclidean space in this graph, and this Laplacian somehow approximating the other one. But maybe one way that I can convince you quickly that these things are related, you know, is the following. Take an integral, or wherever the main, right? I'm not too worried in being very precise, of the norm of the gradient squared, right? You're taking the integral of the size squared of the differences. Right? Look how much this is like exactly how we define the Laplacian, right? Remember here, I'll write it here again, x transpose LGX was equal to sum I small j wij. Right? Integrating, you know, differences squared is very much like summing differences squared, right? Just in sort of a different geometry. Okay, so what is this? Let's take the integral sum of I from 1 to d. Let's say we're in d dimensions. Derivative of f over derivative of xi, right? Squared. Now we can do integration by parts, right? One of the terms gets an extra derivative, the other loses a derivative. So we'll do, right? We have some boundary terms minus, right? The integral, the sum I from 1 to d of f, the term that went up in the integration by parts, and the second derivative. Right, but now what is this? Now this is exactly what we usually call the Laplacian, right? So let's see. Right, this is integral of f times the sum from I from 1 to d f xi squared. But this thing here, right, is exactly the Laplacian of f. Right? So this means that this is exactly the same as, boundary terms minus integral of f Laplacian of f. And so even though it's not quite the same formula, you can already see that these things seem related, right? This is a bit like integrating the difference and summing the differences squared. And this is a bit like an f Laplacian f, which looks a bit like an x of Laplacian x, and there's a reason for this to be the case. But for now, let me just leave it at that. Okay, so what do we know about the Laplacian? Let's write sort of the important equation again. Let's start by noticing things that we know about it. So first of all, I claim, right, the Laplacian is positive semi-definite. Right? All its eigenvalues are either 0 or positive. There's no negative eigenvalues. Why? Okay, an equivalent definition to that is just saying that for all x transpose L gx is negative. And this is obvious from here, right? If I put any x, I just have a sum of squares times a positive or non-negative number because the weights can be negative. And so for sure the Laplacian is bigger or equal than 0. There is positive semi-definite. Right? All its eigenvalues are 0 or bigger. In fact, it has an eigenvalue at 0. Right? It's not easy to see, it's not hard to see that there is an eigenvalue at 0. Right? How can we see that? Well, if we just take x to be the whole one's vector, right, then it's clear that 1 transpose Laplacian 1 is equal to 0. Right? Or even, right, because if I have the same value here in the quadratic form, I get 0. It's also not hard to see that Laplacian 1 is 0. Right, because if you see what happens in a row, you'll get the sum of the weights and then minus the sum of the weights, and then you have to add the degree. And the degree minus the sum of the weights is just 0. Now, a natural question then is, when is it that lambda 2 of LG is also 0? It's a natural question. We know the smallest eigenvalue is 0. We know all of them need to be bigger or equal than that. When is the second one 0? So let's say that we have a set S. Let's say that there exists a set S such that cut of S is 0. And S is not empty. Right? Let's say that there's a set S. Let's call it such that the cut of S is 0. And what this would mean is that if I take x to be 1s minus 1sc, so I take the value 1 in s and the value minus 1 outside of s, then right? Because of the equation we have, the relation between the quadratic form and the cut, we get that x transpose LG, x is 0. So this is already hinting at the fact that if there is some set, if the graph is disconnected, if there is some sense that this is completely disconnected, so maybe I should draw the picture like this, right? There is no edge in between, then there's another vector that lies in the null space. And if neither S nor S complement are empty, then this vector is not a linear combination of ones, right? These entries will be different, and therefore lambda 2 will be 0. Right? So we already get sort of a theorem that's relating spectral properties of these matrices with geometry of the graph. If G is disconnected, then lambda 2 of LG is 0. Okay, basically we just prove this. Okay, homework. Prove the converse. Right? If lambda 2 of LG, if G is connected, then lambda 2 of LG is not 0. Right? Okay, so I want to prove it here. It's not so difficult if you think about it. But here you're already seeing that the second eigenvalue Laplacian is really telling you about the geometry. Right? It's telling you if this graph is connected or disconnected. And you're also already starting to hint at the fact of what spectral clustering is going to try to do, right? Because it's saying that eigenvalues or eigenvectors are going to tell us about what is a good clustering for the graph. And this is not so surprising now, right? Because we're seeing that the second there is another sort of eigenvector with eigenvalue 0 in the Laplacian. And that one has its, if the graph is disconnected, that one has information about S, right? Because if there's S and S complement that are not connected, right, two disconnected components, then the X given where it's 1 in one of them and minus 1 in the other will be an eigenvector with eigenvalue 0 as a Laplacian. And so maybe if you see an eigenvector with eigenvalue close to 0 as a Laplacian, it will encode somehow in this similar way the sets that are almost disconnected. Right? And this is exactly the idea of spectral clustering. Okay, but let's talk first a little bit about clustering in general. Right? So clustering is sort of the main, it's almost like the thing you do first when you're doing unsupervised learning. If you get data and you don't know much about your data, the very first thing one considers to do is just cluster it. Split the data into different into groups. Right? So let's draw a picture, just take an example. Right, let's see I have data that looks like this. Bigger one. So we get data like this. It's very nice. I mean, I made a very nice data, right? And so it's very easy to see what the right clustering should be. Right? The right clustering should be this. Of course, this is one cluster, this is one cluster, and this is one cluster. And then, if you're doing data analysis, you should just look at each cluster and see what. Now we can look at the geometry inside this one and so on. But the first thing would be to just split the three, and then look at each one separately. Right? This is the first step would be clustering. Now the sort of the most popular and maybe the simplest algorithm in clustering is called k-means. Right, so k-means clustering. So k-means clustering really exploits Euclidean space, right? These points are here on the plane or in Euclidean space. K-means clustering really exploits this, and it does the following: it tries to cluster by assigning to each cluster a center. Right, so it clusters. Okay, clusters. Right? Euclidean data, so x1, xn in say d dimensions in k clusters. Okay. By assigning to each cluster a center. And then just assigning points to the cluster with respect just by which center it's closest to. Right, so let me write an actual objective. So this is now known as the k-means objective. Right, so you minimize over all possible centers. Right, k is 1. Right, these are points in RD, of course. And now also partitions. Okay, and now you minimize the sum over the clusters. Now the sum over the points in the cluster. And the sum of the square of the square of the distance of the points to the center. Okay? So basically for every single point, you're assigning it to its closest center, and you're trying to minimize the sum of the following. Over all points, take the distance between that point and the center of the cluster you associate with, sum the squares of that, and you try to minimize this. Now the issue is that minimizing this is hard. Right? The minimizing this is hard. Right? So minimizing this is hard. Now, there are algorithms to attempt to do it. And when people refer to k-means, oftentimes actually what they mean is the algorithm that's called Lloyd's algorithm. So Lloyd's algorithm is a very popular algorithm for k-means. Lloyd's algorithm does the following, right? It starts with the following observation. If the centers are given, for one, if the centers are given, then assigning clusters is easy. Right? If the centers are given, then assigning the cluster is very easy. For each point, you just get it to the closest possible center. Also, second observation, if clusters are given, then computing centers is easy. Why? Because if you have the clusters already done, then the center is just, all you have to do is minimize the sum of the squares of the distances of all the points to the center. And this is actually the mean of the points. Right? So given these two observations, a very trivial, naive algorithm would be to just do alternating optimization between the two. Right? So do alternating optimization. Right, so one, assign clusters based on centers, just by going to the closest, each point to the closest center. Two, compute means of clusters, and now repeat. Right, so you start with some centers. Now this assigns some clusters. Now you look at the cluster and say, maybe I can compute better centers. So you go and now take the centers of the clusters that you have. This now gives you new centers. So now maybe the clusters will change if you optimize the clusters. And then you do this back and forth until it stops moving, right? Until repeat until convergence. Until it doesn't change. Right, and So this is a very classical type of idea of if you have, it's like a chicken and egg type thing. The clusters would be easy if you knew the centers would be easy if you knew the clusters, but both at the same time are hard, but what you do is just fix one and you keep iterating between the two. Okay? So actually a very nice homework problem is to just try this. So just, generate some random data or some data that you like, anything, and just try it. Implement it and try it. So k-means has many issues. One issue is that, well, optimizing that is hard, so we don't know if this actually converges to the right solution. It might not. And in many cases it doesn't, right? It might get stuck in all sorts of local minima. There's many algorithms to try to remedy this. By maybe like once it gets to a local minima, you wiggle it a bit, try to get out of it, and try to change a little your centers maybe, or there's all sorts of heuristics. Another thing you can do is try to start with good first centers, so that to try to avoid as much as possible getting stuck in a local minima. This is basically what an algorithm known as k-means ++. That's oftentimes what's implemented actually. That's what it does. It just starts with centers that are sort of, at least they're far away from each other, say, just so that being stuck in local minima is less likely. But still, there's no guarantees, and in general, it will be stuck in local minima for some types of data. But a different issue, right? There's these computational issues, but there's another issue, which is k-means only see sort of linearly separable or convex data. Let me give you an example. Let's say that your data set looks a bit like this. Right? Or like this. I claim that probably the right clustering algorithm here would be to cluster, the inside points belong to a group, the outside points to another, and here that one of these half moons belongs to a group, and the other half moon belongs to the other. But k-means would never have a hope of doing this, right? If you start thinking where the centers would go, there's just no way. Another way to see this is that once you have the centers, the way you assign clusters is just by giving to the closest center. This is just bisecting the space, right? You just separate the space between the points that are closest to this point or this point to just get a line, and you cannot separate these things with a line, right? So then the question is, how do we cluster these, right? How do we cluster this type of data? Right? How do we cluster this type of thing? So there's many ways around this. One way is you could try to add dimensions to the data. For example, let's say here, I have this data in 2 dimensions, but I could say I'm going to add a 3rd dimension, what the machine learners call a feature, an extra feature, where I say, for example, distance to the center. Right? Let's say that this is the center, and now my 3rd, right, I have the x, y coordinates, and my 3rd coordinate is x squared plus y squared. If you think about what happens here, then these points will start coming out of the board, right? This is the z-axis. These points will start coming out of the board, and these ones not as much. And so you can easily now cluster this by just clustering on the z-axis. Right? And there's a whole industry of coming up with ways of doing this, right? Of adding features so that you can cluster, so that you can embed in space in a way that it becomes separable. This is the idea behind things like kernel PCA and so on and so forth. What we're going to do is a little different, although not so different, but motivated in a slightly different way. We're going to think of just grabbing this data and making a graph with it. Right? So, for example, one thing we could do is just look at this data and think of just connecting, just connecting data points that are nearby. Think of each data point, we make it now a vertex of a graph, and we connect things if they're nearby. Right? So we can't connected, and maybe even sometimes we might make a mistake, and there's some data here, things don't cluster perfectly, and we get something like this. But it's clear now from the viewpoint of the graph, this is still a small cut, right? So it might still work that this does quite well. And the same thing here, right? If I'm lucky, I'll cluster this in one connected component of the graph, this in another. Maybe there's some low jumps or something, but they should be small. Maybe then if I cluster the graph, if I run something with a low cut on the graph, I will actually be able to cluster this data. Right? So one way to build graphs, I mean, you could do, there's many ways. There's like nearest neighbors. I could say for every node, I connect to the 5 closest neighbors. And there's a lot of research that goes into algorithms of how do I compute very quickly nearest neighbors, even with very high dimensions and all these things. But one way is through a kernel. I can say, for example, I build a graph where the weight of the edge ij is, say, exponential of so now, what am I doing? I'm saying if points are very far away, much more far away than epsilon or than square root epsilon, then their weight is going to be really, really small, right? It's exponential of minus something. And if their distance is in the scale of epsilon, they basically get a real edge with weight 1. Okay? And in general, it's this idea that I can do with the general kernel. This is big. This is what's called the Gaussian kernel, right? You have the Gaussian kernel, where you get something like this, right? Some kernel depending on epsilon, it should be very high or close to 1 when the difference between these is in the scale of epsilon, and very close to 0 if they're not, if they're in some other different scale. Right? The idea, this is also the basis for something called manifold learning, right? If I'm trying to learn a manifold, right, to learn a surface or something like this, then I can think, if I'm trying to learn a manifold, a surface, let's say that I have this surface, I want to learn its geometry, but it's curved in space, right? And I want to learn how, like an ant walking around in this page, what is the geometry that the ant sees? Then it's a bit like this, right? In the sense that I can trust very small distances. So these 2 points are very close in ambient space, and these 2 points are very close in ambient space, and so on, and they're also close in the page. But distances of a bigger scale, like this distance, I cannot trust, right? If I have 2 points at this distance, then they might look at this distance in ambient space, but in the sheet of paper, they have to go much, much further. And so you should trust, when you're doing manifold learning surfaces, because your space might be warped, as this clearly is, then you basically should trust small distances at scale epsilon. This is exactly what this is doing, and not trust long distance. This is exactly the idea behind this, behind manifold learning, and behind diffusion maps that we'll see. Right, but the idea is build a graph. Right, build a graph and cluster the graph. And now we have to learn how to cluster the graph. Right? How do we cluster graphs? Right? So we can say, well, the natural thing to do would be, find the minimum over all subsets of vertices that minimizes the cut. If you think about it a bit, then the way to minimize the cut is very easy. You just take S to be either the whole graph or S to be the empty set. Right? So if you take that, then the cut is 0. So just minimizing the cut is not interesting. Right? This will not be a good thing to do because you're getting a completely boring solution. So we have to somehow make sure that this doesn't happen. Right? We have to try to minimize a cut that doesn't have, take the minimum cut in some way, but we have to make sure that the cut is in some form balanced. Right, so here's one thing we can do. We can force, say, that the size of the size of the set that we're minimizing over is, say, half the edges, the number of vertices. So let's say that the number of vertices is even from now, and we just take S to be a half sum, right? So now we can say, well, then I want to minimize over all S is a subset of the vertices, whose size is 1/2 of the vertices. And now I can minimize the cut. Okay, this is what's known as minimum bisection. Right? This is the problem known as minimum bisection. Let's try to understand it a bit better. So let's try to relate it to the Laplacian. Right? Let's take x to be 1s minus 1s complement. Right? X is just 1, right? It's the indicator of x in the sense that xi is 1 if I is an s and minus 1 other s. Okay, so now we know that the cut of s is equal to 1/4 times x transpose Laplacian x. Right? So this means that if I'm trying to minimize the balanced cut, I could instead minimize this, right? I could take the minimum over x of this form. Let's go to it in a second. Let's take the 1/4 outside of x transpose Laplacian x. Now, what makes x be of that form? Right? So let's try to define a set that classifies all x's of this form. So we have to have x being hypercube. Right? X is plus or minus 1, right? Because that's definitely the case. And once x is plus or minus 1, it will have to be on that of that type, right? It's just 1 in S and minus 1 in some S complement, and some S and some S complement. The fact that it's balanced is just meaning that x transpose 1, let me write 1 transpose x instead, that 1 transpose x is 0. Right? This is what I'm asking. It's completely equivalent. Finding a minimum bisection is completely equivalent to this. Okay, but now, if I do, okay, this is still not something I can, right? It's starting to look spectrally, right? If you remember in PCA and so on, you were maximizing symptomatic form, right? Minimizing instead of maximizing is just a minus sign away. But this is a strange constraint, right? Being in the hypercube. But what if we relax that? What if instead we replace with the following: 1/4 minimum, right? Something a bit more spectrally looking, right? The 2 norm being square root n, and 1 transpose x being 0, x transpose LGX. Okay, so let's look at this. So if x is in the hypercube, then for sure the ultimate norm of x is square root n. Right? So this search space is bigger than that one. So immediately, because we're minimizing, since the search space is bigger than that one, it means for sure that this must be smaller or equal than that. Right, but let's keep going, because now this is starting to look like an eigenvector, eigenvalue problem. Right, so let's just make this on the scale of 1. Right, let's take z to be like student. Right, we'll just take z to be 1 over root n x, just to put it at the ultimate norm being 1. Right, this condition is exactly the same, right? The constant times 0 will just be a constant. And now I'll get, right, I'll get root n z, so an n needs to go over here. Okay. Now let's think about what this expression is. I'm minimizing this quadratic form, which is like taking the smallest eigenvalue, right, over the sphere, and I'm making sure that it's orthogonal to the whole one's vector. But the whole one's vector is exactly the minimum eigenvector of LG, right? We saw that LG was positive semi-definite, and 1 was its in small space. So if I'm minimizing the quadratic form subject to being orthogonal to the first eigenvalue, what I'm doing is exactly calculating the second eigenvalue. Right, times n over 4, of course. Right, this is exactly the second eigenvalue of the Laplacian. Okay, so it's already starting to look, right, the eigenvalues are starting to show up. Right, in particular, we immediately get an inequality. Immediately we get that n over 4 times the second eigenvalue of the Laplacian, right, is for sure smaller or equal than the minimum bisection. Right, this is already, I think, a very non-trivial inequality that we got with almost no effort. Now, a reasonable strategy right, if what we want to do is minimum bisection, we now have a reasonable strategy. Right? We compute the minimizer of this, right? Let's call it V2. Let V2, right, be the argument. I'm calling it V2 because it's the second eigenvector of G. The argument of that problem, right? Of V2 having 1, V2 transpose 1 transpose V2 being 1 being 0, and V2. Okay, I don't need to use the letter V2 when I just use Z. Right, so if V2 is always plus or minus 1, or in this case plus or minus 1 over root n, then it's obvious what to do. Right, you would just say the plus 1s become S and the minus 1s become S complement. Right, if it is, then we're done. Right, basically S, the set where of I such that V2 entry I is bigger than 0 is the minimum bisection, is the solution. And if we're close to this, it's also clear that something like this probably works. So a very reasonable strategy is to just do the following. Take V2, right? And now, since we're doing bisection, we just take the smallest, the indices. So indices with, or n over 2 indices with largest value are S and rest as complement, right? So this is a very reasonable strategy to try to now cluster. We just saw that this thing somehow related to a spectral problem. Right now we solve the spectral problem, we have V2. If it was just plus or minus 1s or 1 over root n because of the scaling, then it's clear, right? The 1s belong to S, the minus 1s belong to S complement. In general, it will be whatever. One thing we can do is just say, well, the first n over 2 of them are in S, the other ones are in S complement. And this will give some bisection. And this may or may not give a reasonable bisection. But we're going to show in the next lecture is that indeed this will give a reasonable way of clustering. What we're going to do, however, is not force the clustering to be a bisection. Because if you have real data, it might not make sense to make the clusters necessarily the same size, right? We want some leeway around this. And so we're going to have a way of defining cuts in a normalized form in a way that neither we go into the boring solution where the optimal solution is empty, nor do we go in this very brittle sense in which it needs to be exactly a hull. And then we're going to look into a relaxation of this type and what a thresholding or rounding, right? We call this relax and round. Why? Because we have an original problem over a difficult set with hard constraints. We then go relax it into something a bit softer that we can now optimize because it's a spectral problem. And it's a relaxation because the optimization set contains the other one. And then we get the solution of that. It looks like all over the place, not just necessarily plus or minus 1. And so we grab it and we round it in some way. Maybe we take the sign. Or in this case, because we know exactly one n1 over n over 2 on one side and n over 2 on the other, it makes a lot more sense to just take the n over 2 largest and n over 2 smallest. So in the next lecture, we're going to see how to do this, how to define this in a more soft sense, and guarantees on this algorithm, also known as Shiger's inequality. Thank you.